Hello. It is December 24th, 2018, and my name's Tim Burton, and today we're going to discuss the 432 frequency characteristics. And so we're going to go over the current 440 system that we use, the current 432 system that I've been using for the last 4 years, and we're going to discuss the 432 perfect pitch pure tones. And then we're going to get into the pure tones with the 369 code in it. And then we're going to get into the difference between 432, the current system that we use, and then the pure tones, which are similar, but there's just a little bit of difference, a little bit and a lot of difference in some areas. So that's what we're going to discuss. Okay, so in this clip, we've got the 440 iOS 16 current. This is the current system that we use today. Now, iOS, what does that stand for? That stands for the International Organization of Standardization. So the 440 iOS system that we currently use, I'm going to show that it's flawed. It's flawed. I mean, it's worked for however many years, 50, 60, maybe 60 years, but it's flawed. And when I say it's flawed, harmonies are precise, and I mean they're precise right down to the decimal, and there are no harmonies in this current system. There are no harmonies in this system. These are all harmonies. And this is so what we've got here is we've got the 440 system. We've got a 432 system, the iOS system. Like if you tune your guitar to 432, then there's no harmonies. It's close, but there's still no harmonies. Whereas if you it's impossible to tune your guitar to this system, to a pure system, because the guitar's frets are set. It might be possible to tune a piano to this, but I don't have a piano, so I haven't tried. But I know I do have a keyboard synthesizer, and you can put your synthesizer in 432, but as soon as you get to the C or the C sharp, you're out by this much. So in the next clip, I'll get into that. Anyways, all I want to do in this clip is show that there's a certain amount of hertz, there's a certain amount of frequency that's in between these notes. And what I've figured out is that there's exactly 24 hertz in between the first 6 notes of the 432 octave that we're looking at. And the second 6 notes has an exact amount of 36 hertz in between the notes. So what I'm going to just do on this clip is show how I derived at this right here. So when you're looking at the 440 system or this system here, the iOS gives you these frequencies to tune your instruments. The manufacturers, they provide this data, but nobody uses this data for the instruments themselves. And what I mean is, I went and saw a music theory teacher, and and I also talked to a piano tuner for 15 minutes, and it was very clear talking to both these people that they don't deal in terms of number frequency. They deal with just notes, and then all the corresponding stuff that comes along with it. So it's to me it's very important that you realize that the frequencies themselves are very important. So anyways, like I said, I'm just going to show you right now how I derived at these numbers that show the perfect pitch tones. So if you're looking at the 440 system, you'll notice that these frequencies that are in between the 440 system are all, it makes it look like as the frequency goes up, the frequency in between the notes goes up. And whatever, that's fine. It's not. That's not the way it's supposed to work. So I'm just showing you that what I did was I eventually took the first 6, I averaged them all out and got, something like, around 30. And then I ended up figuring out that if you take the first 6, you get around 25. You take the second 6, you get around 36. 36 ends up being the number. And then it's the same with the 432 iOS system is, this works out to about 25, 35. So I eventually figured out that in order to go from 440 to 415, look at it's 24.7. In order to go from 440 to the A sharp, the 466, there's 26. And so I did that with this one too, and I got a 24 and a 25. So I eventually, I spent 2 weeks, 10 hours a day on this, and I eventually came up with the 24. And it'll make a lot more sense once you see the next clip and you see the 369 code in there. But so anyways, the increments themselves are, it's very clear that, like if you want, the thing is that this is perfect harmony right here. There's perfect harmonies between, musicians will know that, like, you play an A major chord is an A, C sharp, and an E. I've already proven to myself, and I'll do an entire video on harmonies, that the A, the C sharp, and the E are all perfect harmonies in these frequencies right here. So now one of the things I want to cover in this clip is why I'm starting off on G. And the reason I'm starting off on G is just because of the increments. There's a note right here. It's F sharp equals 360. And that's a key thing to note, because 360, represents a circle, 360 degrees. So there'd be a 12 here with a F sharp equals 360. I'm not including it because I'm including the F sharp as the end of this octave. So this 24 up here represents the 360 to the 384, and then there's 6 of them. So there's 6 and 6. Now if you look at this octave up here and this octave down here, these numbers start changing. Like it goes down to 18 for these 6. And it goes up to, I believe it's 48 for these next 6. And then it changes to 72 for the final 6. But the point is that that's why I'm starting off at G, is because these numbers denote that there's a 6 pattern in the octave itself. And that's why I'm starting off at G. Now, the other thing to note is that if you take this G and you go up to the next G, which is an octave, or if you let's do it this way. If you go F sharp, this 12 F sharp equals 360 to this, that means there's 360 hertz in between this note and this note. 360 hertz. So these have to add up to 360 hertz. And that's what they do. They add up to 360 hertz. So that's another way to look at why this is a, it's a perfect system. And a final note on this is that look at it and look at this right here and see that there's a design. And there's no decimal places, decimals, no decimals. Okay, so this right here is a perfect pitch, pure tones. Okay, in this clip we're going to go over the pure tones. Here's 3 octave of pure tones, and then we're going to add in. We're going to talk about the 369 code that's embedded in these octaves, in these frequencies. So what we've got here is we've got the 432 12 note octave right in the middle here, and then we've got an octave above and an octave below. These are all pure tones. You won't find these in any instrument. You won't find these in any literature. I've never seen these tones, but this is based off of the 432 tones, and so we're just going to talk about some of the characteristics. So how do you come up with? My first video I did was solely on the 369 code, how I use it and why I use it. So if you want to know more about the 369 code, this stuff right here, then there's a whole video dedicated to it. So I'm not going to go into that, but I am going to go into where briefly how these numbers are arrived. So if you go 3 plus 8 equals 11, plus 4 equals 15, 1 plus 5 equals 6, 4 plus 8 equals 12, 1 plus 2 equals 3, 4 plus 3 equals 7, plus 2 equals 9. So that's how you come up with all of these numbers. Now what these numbers show is they not only show the numbers that you add them up to, but they also show a pattern. And so here's the pattern that they show. They show a 639, 639. Now because they're grouped in threes here, I've put a line here, and I've also put a line here and grouped these into threes, even though you could group them into 6, but I've been doing this long enough now that I realize that, you can see certain characteristics, which mean that because these are grouped in 3, these are grouped in 3, then, there's 99.9% chance that these are grouped in 3. So that's why there's a line denoting that. Now, you can also cut this whole octave in half by showing that there's 24 hertz in between these first 6 numbers. There's 36 hertz in between these numbers. So that's another reason that's a characteristic which you can show that shows that the octave itself is split in half just because of these numbers in the half, and then you can split it into threes because of these numbers. That's all it's showing, is just a characteristic. So one of the things I found in doing all this is that these notes here, this one line of code shows one code, but then when you go up an octave, it's different. It's slightly different. So then in this one, you've got a 369, 369. So you've gone from in the 432 code, the 432 octave, you've gone from 369 or 639, 639 to a 369, 369, 999, 999. Now, so what that means is that this is one cycle. This is one cycle. That's another thing that the 369 code does. Besides it showing that you can split this up into threes, now it's showing that you can combine 2 octaves into one. It's one cycle. That's one cycle is shown by the 369 code. So if we go down an octave, it's just showing the last part of this cycle of an octave, which is just showing 369, 369, 999. So I'm just showing that these pure tones with their corresponding increments, and that's another thing you should notice is that, so you've got 24 in these first six, 36 hertz in between these six. You've got 12, half of when you go down an octave, you're going half of the increments. And then when you go up an octave, you go up double the amount of increments. So here's 12 in between the notes, 18 in between the notes, 24, 36, 48, 72. Now, the final part of the code, which I found in this right here, is if we stick with the 432 octave, there has to be a jump up, because you've got to go, when you're dealing with a full octave, you're dealing with, in this particular one, you're dealing with 360 hertz. Makes this would be different, this would be different, but this one adds up to 360, meaning it's like a full circle. It's like the degrees in a circle. So with this one, you've got 24 for the first six, you've got 36 for the second six. So 36 minus 24 equals 12. So that denotes how much you're adding to get to the next six. Same with here and here. And also point out that this is exactly half, this is exactly double, just like these right here. So anyways, when you're doing the 369 code, you go 2 plus 4 equals 6, 1 plus 2 equals 3, 3 plus 6 equals 9. Now, 639, where do you find that? Where do you see that? Right here. 639. Okay, it's a design. That's all it's showing. This whole thing's designed. It's designed by who? I don't care. I'm just saying that the design was always there. It's been there since the beginning, but it's designed. It's designed just like you design a anything. But so that's all this is showing. So you go over to this one, 369, 369. You go to this one, 369, 369. Okay, on this final clip here, we've got, I'm going to show you the difference in frequency between the 432 iOS. This is the current system that we use. Here's the pure tones that everybody will be using in the future. And I'm going to show you the differences and the characteristics, some of the characteristics of the differences in frequency. So all I did with this is you take the 384, or you take this number here, you take 384.87 and you minus 384. This is a pure tone. This is a 432 iOS system, and you subtract that, you come up with 0.87. Same with this one, 408 minus 407.75, 0.25, on and on and on. Okay, so as you can see, these are just the differences between a pure perfect pitch system and then this current system that we use. So in the current system that we use, what it's saying is that these are perfect harmonies. I've tested it. I've been a musician for 40 years. I've tested it by recording it and looking at the sine waves. I've tested it numerically. This is a perfect system. I'll do an entire video on harmonies themselves. But the whole point of this video is just to show how much this system is out. The 440 system that I showed you in the first clip, it's the same thing. It's even worse than this system here. But this, I'm just showing you that these are out now. The big thing I want to show is that, okay, so the G sharp is only out by 1/4 of a hertz, but it's still out. I mean, I know a lot of musicians who would rather be dead on. You know what I mean? Like, there's some musicians out there, fanatics, that if they know that there's a system that is pure, they're going to want it. You know what I mean? So anyways, as you can see, these are all out except for the 432, obviously, but all the rest of them are out. Now there's four notes that stick out the most. Okay. Like you've got less than 1 hertz. You got a quarter of a hertz. You got, this one's right on. This one's less than 2 hertz. Okay. And then you get up to here, 5 hertz out, almost 5 hertz out. This one's almost 10 hertz out. Down here, you got a 4.3 hertz out. Okay. And then you've got to go all the way down to the F sharp, and you're out by 6.5. Now, I've been doing this for a couple of months now, and when you see something like that, you tend to want to know why. So why are these four notes out by so much? And anyway, so I spent about a week trying to figure this out, and I came up with, I'll show you what I came up with. Okay, and this is what I came up with. And what you're looking at here is this, you can call it whatever you want. Note wheel, note circle, frequency wheel, frequency circle, doesn't matter. But these, if you look at a clock, it goes 1 through 12. Well, if you look at these tones, 1 through 12. So that's all I did here was I went 1 through 12, or G through F sharp. And then I just lined up from the middle. I went B, C, C sharp, and F. Now, I'm just showing you this for whatever reasons. I'm just showing you that this is what I've got. This is what I initially got when I tried to figure this out. Since then, I've been able to add color and the four elements, fire, earth, air, and water. I've also been able to add in, but those are completely separate videos. So all I'm showing you is that this, because I don't believe that, we think of this as the peace symbol. I believe if you go back in time, this is actually the earth, the fire, earth, air, and water symbol, tying in these notes and the colors. But that's for, like I said, this will be a completely separate video just on this stuff with the color and the other stuff tied in.